Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about the slope of a curve. We're actually going to be starting calculus, and a very important concept in the area of differential calculus is the idea of slope of a curve. So before I talk about slope of a curve, I just want to review the slope of a straight line. I did do a video on slope of a straight line or linear functions. I'll just do a quick recap here. So when we're finding the slope of a line, we take the difference in the y values, or the vertical distance called the rise, and we divide that by the difference in the horizontal distance called the run. So the slope of a straight line is equal to the rise over the run, which is also defined as the rise is the difference in the y values, so y2 minus y1. Run is the difference in the x values, so x2 minus x1. And another way we can think of it is the change in y. Delta is a Greek symbol that we use to represent change. So when we say delta y, it means the change in y over the change in x. So that's nothing new. What I want to do is talk about this, but I want to name my points a little bit differently. So instead of x1, y1, I'm going to call this point x and f of x. Now I've talked about function notation and functions in a previous video as well. But remember, y can be thought of as a f of x. Okay. Then what I'm going to do with my next point, I'm going to call the run. I know that the run is delta x. So instead of defining my x value as a different value, I'm going to write it in terms of x. So this x value will be x plus delta x. Okay, so I take this x value here, add this change in x, delta x. So this whole distance here will be x plus delta x. And then my y value, instead of writing it in terms of y, I want to write it in terms of x. So it will be f of x plus delta x. So it'll be the function of this x value. Therefore, I can think of my slope in terms of these points. We know slope is delta y over delta x, rise over run, but I'm going to express delta y as f of x plus delta x minus this y value, which is f of x over delta x. That is another way to express the slope of a straight line. It's important to note that the slope of a line, of a straight line, is constant. It's the same at any point on that line. It never changes. And the slope refers to the rate of change of the function with respect to the independent variable. I want you to be comfortable with that and not intimidated by that notation, because we're going to use that when we talk about slope of a curve. Slope of a straight line is constant, but slope of a curve is not. Let's take a look. If we take a look at a curve, any curve, the slope of the curve is going to be different depending on the point of the curve. So the slope here is actually a very steep slope. Not so steep here, not so steep here, and flattening out even more here. So the slope actually refers to the instantaneous rate of change of the function with respect to the independent variable. And you're going to hear me use that terminology quite a bit. Now, again, I have labeled this point x and f of x. I've labeled this point, the x value is x plus delta x, so here's my x and here's my delta x. And the y value will be f of x plus delta x. So I kind of wrote the notes out here of what I'm going to say, just so that you've got a visual as well as hearing what I'm saying. But to find the slope of a curve, we move m closer and closer and closer to n. And when we do that, the slope of the line mn will more closely approximate the slope of a tangent line at point n. And a tangent line is a line that touches the curve at one point only. It does not pass through the curve. So the tangent line would look like this in this case. The slope of that tangent line will actually be the slope of the curve at that point. So we have to move m closer to n, but we can't actually let it be the same point because we need 2 points to define slope of a line. So how do we get m closer and closer and closer without it actually being that point? Well, we've talked about how to approach something without actually equaling it, and that involves the idea of limits. So here's the definition. This is key in understanding the slope of a curve. And it will also be key in understanding the instantaneous rate of change of a function. And it will also be key in understanding the derivative of a function. So let's talk about the definition. The slope of the tangent line to a curve, which is the same as the slope of the curve, is the limiting value of the slope of the line mn as m moves closer to n. So we're going to get into limits, and we have to express the slope of the tangent line as the limiting value of the slope of mn. So how do I express the slope of mn? I take the change in y over the change in x, and I'm finding the limiting value as the points get closer to and closer together. So in other words, as delta x approaches 0. So when m gets closer to n, the change in x gets smaller and smaller and smaller. We want it to approach 0, but we can't let it equal 0. Otherwise, we won't have 2 points. And how do I express that in terms of my 2 points? It's the limiting value as delta x approaches 0 of my change in y values. So this y value is f of x plus delta x minus this y value, which is f of x, over delta x. That is the slope of a tangent line to a curve, which is also the slope of the curve. So let's take that definition and apply it to an example. So my example says, find the slope of the curve f of x equals x squared at the point x equals 3. So I've drawn y equals x squared, or we can call it f of x equals x squared. And I want to find the slope of the curve at this point here. What I want to do first is find the formula for finding the slope of the curve, and then I'll find it at that specific point. The advantage of that is that once I've got the formula, then I can find the slope at any point on that curve. So to find the slope of the curve, I find the slope of the tangent line to the curve, and I'm going to use this formula. Now remember that if f of x is equal to x squared, then f of x plus delta x will be x plus delta x squared. That's going back to some work I did on functions earlier in an earlier video. And when I expand that, remember it's going to be x plus delta x times x plus delta x. I FOIL that and it will be x squared plus x times delta x plus x times delta x, so there's 2 of them, plus delta x squared. We don't need brackets there because it's usually understood that when you see delta x, it means one variable. It represents a change in x, which is one variable. So I'm going to plug this into my formula for f of x, and I'm going to plug this into my formula for f of x plus delta x. So the slope of the tangent line will be equal to the limiting value as delta x approaches 0 of f of x plus delta x, which is this, x squared plus 2x delta x plus delta x squared, minus, so that's this whole thing, minus f of x, which is x squared, all over delta x. In order to evaluate this, remember that when we're finding limits, we look to see if the function is continuous at this value of our variable. Can we put a 0 in for delta x? No, we can't. It's not continuous. So our next step is to try to simplify this to a function that is continuous at delta x equals 0. So I've got x squared minus x squared, which is 0. I have 2x delta x plus delta x squared over delta x. I still can't put a 0 in. However, I can factor my numerator. And I'm going to hope that by factoring my numerator, I can simplify. So when I factor a delta x out of both terms in my numerator, I end up with this. And then I have a factor of delta x in the numerator and in the denominator, so I can cancel. I had to erase a bunch of things to be able to fit this on, but when I cancel the delta x factors, I end up with the limiting value of just 2x plus delta x as delta x approaches 0. Is this continuous when delta x equals 0? Yes, because the denominator is not there anymore. So therefore, I can evaluate the limit by putting a 0 in for delta x. So I'll have 2x plus 0, which is 2x. That's the formula for the slope of the tangent line to this curve. The question asks me to find it at a specific value. So at x equals 3, what's the slope of that tangent line? So at x equals 3, the slope of the tangent line will be 2 times 3, which is 6. And once I have the formula, I could find it at any value of x. That's how we apply this formula. It's a lot of work, and I'm going to do it in some more examples. On the next video, I'll talk about instantaneous rate of change of a function, and we're going to come back to this formula again. The video after that, we're going to talk about derivatives. We'll come back to this formula again. So hopefully I didn't lose you too badly, and hopefully the next couple of videos will help. All right, take care, and we'll see you then.